Welcome back to my channel. This is part 3 of our Introduction to Calculus series, and today we're exploring sequences and series. Let's get started. Let's plot integers in the number line, and let's choose some of these integers. We're starting on number 3 and jumping 2 and 2 and keeping on and on. In mathematics, this is called a sequence, and, as you can guess, this follows a rule. But which rule? Well, we can see that it jumps 2 every time. So, our rule is something like 2 times n, where n is an integer. It's close, but not quite. This sequence starts at 2, but ours starts at 3. Instead of 2 times n, let's try 2 times n plus 1. Bingo! We have calculated the first, second, third term, but we can calculate any term, for example, the 50th term. Usually, sequences are represented by an, where n is the index. In this case, n is 50, and the result is 101. As we have seen, the difference between one term and the next is a constant. That's why this sequence is called an arithmetic sequence. And the formula is this one, where a1 is the first term, n is the index, and d is the constant. In our example, a1 is 3, d is 2, and the sequence is calculated as expected. Note that we are multiplying the constant by n minus 1, because d isn't used in the first term. Another type of sequence is the geometric sequence, also called geometric progression, where each term is found by multiplying the previous one by a constant, called the common ratio. This formula only works when n is more than 1. If n is 1, we have the first term. When n is 2, we multiply the first term by the constant. When n is 3, we multiply the second term by the same constant. Now let's replace a2 by the last formula. It's like multiplying the first term by the common ratio squared. Let's do the same for a4. This time, the constant is raised to the power of 3. So, we can say that each term is found by multiplying the first term by the common ratio raised to the power of n minus 1. Now, let's use these two formulas to calculate the geometric progression when r is 3 and the first term is 2. The first formula first. We're calculating the first 5 terms, but feel free to try more. And now, the second formula. As you can see, and as expected, the result is the same. Our geometric progression is this one. Well, at least the first 5 terms, no matter the formula you use. Have you ever heard of triangular numbers? They represent the number of dots that form an equilateral triangle when arranged in rows. If we add another row of dots and count them all, we'll get the next number in the sequence. We can also use the following rule, instead of counting each dot. Other famous numbers are those that form the Fibonacci sequence. It deserves its own video. But for now, just remember, you get the next number by adding the 2 previous ones, starting with 0 and 1. This type of sequence is called recursive because it depends on more than one previous term. Let's go back to our first sequence. And let's sum up the first 5 terms. This is called a partial sum or finite series, and it's represented by the following symbol. In this case, the partial sum goes from 1 to 5, and the result is 35. We have seen that a sequence can be more than 5 terms. It can go on forever. When that happens, we use this symbol to show it goes to infinity. This is called a series, or more specifically, an infinite series. But what is the result? Well, we don't know. It just keeps growing without end. That's why we say the series is divergent. Take a look at this example. Add progressively the first terms of the series. You'll notice the numbers get closer and closer to 1. So, even though this series is infinite, it's heading toward a specific value. That's why we say this series is convergent. What is the sum of 1 from 1 to n terms? We are adding 1 and 1 and 1 n times. Therefore, the result is n. Replace 1 by another number. It can be 2, 20, square root of 7, even pi. In fact, it can be any constant, so let's call it c. What is the result? As you can see, we are adding c n times. So the result is n times c. Consider multiplying a series ak by a constant c. This is the same as multiplying the whole sum by c. Apply the distributive property of multiplication over addition. We get this series. And we get this rule. Two more important rules are the addition and subtraction of series. Let's start by the addition. And let's represent this series by the sum of these additions. Apply the properties of associativity and commutativity. And we get these series separated. Make the same to the subtraction. What happens here is we regroup the positive and negative terms, which is the same as separating the two series of terms. We've looked at the sum of 1, the sum of any number. Now it's time to see the sum of the sequence of numbers k. Let's call it s and write it in reverse order. Now let's sum these parts. I'm adding each term, so you can clearly see that the result of all sums is always the same, n plus 1. How many terms do we have? n. So, we can multiply this result by n. Divide both sides by 2, and we get this formula. Therefore, instead of summing all the terms, we can use this formula to get partial sums. Does this look familiar? It's the same one we use for triangular numbers. So, if you add up the first 6 numbers in a row, it's the same as counting all the dots in a triangle with 6 on each side. That's why this is called the closed form for triangular numbers. Many series, though not all, have equivalent formulas like this one that make things easier. I won't go through all of them or explain how to get each one, but here are the ones you'll probably see most often. And that concludes our lesson on sequences and series, the last step through advanced algebra. These tools will be essential for understanding what comes next. If you've learned something new today, make sure to like the video and subscribe. I'll see you in the next lesson.